This is Physical Science 2, Chapter 21, Part 4 on the Earth's changing surface. In this portion of the video lecture, we will be discussing geologic time. Geologic time is really the entirety of Earth's existence. And so when we study geologic time, we want to take a look at when and where different geological events and biological events have occurred. And there's a couple of different ways that we can use the Earth itself to figure out generally or more specifically a time of either the biological or the geological event. A way that geologists use kind of an estimate for ages of objects that they find is what we call relative dating. So relative dating places objects or events in kind of the general sequence in time. It's a ballpark estimate. We don't know the exact age of, let's say we find a fossil. We don't know exactly how old it is, but we can use a couple of rules or principles of geology to give a general estimate of the age of that object or event. So in relative dating, geologists follow these rules for relative dating. One of these principles is what we call the principle of superposition. The principle of superposition states that the oldest rock layers are at the bottom and the youngest rock layers are at the top of a sequence, provided that there has been no disturbance in the area. So basically, a fancy translation of the principle of superposition is the further down you dig, the older something will be. So here we have some, in the diagram, we have some of the identified and named layers of the Grand Canyon, which is a great example of kind of geologic time for us to view. So if I find a fossil, for example, in the Hermit Shale, and later on I find my colleague found a fossil in the Red Wall limestone. I would know that the fossil in the Red Wall limestone is older than the fossil that I found in the Hermit Shale because the Red Wall limestone is further down. So the principle of superposition, old stuff is at the very bottom, young stuff is at the very top. So again, in a sequence of relative dating, I know that because I had to dig down further to get the little trilobites there in the bedrock, that those trilobites are older than the clamshells that are found near the surface due to superposition. The principle of uniformitarianism. It's a very large word, but really when you translate it out, uniform means the same. And so the principle of uniformitarianism means that the laws of nature that operate today, they would operate the same way in the past. So an earthquake behaves today just like an earthquake behaved 1,000 years ago, 100,000 years ago, 1,000,000 years ago. Same thing for volcanic eruptions. The way a shield volcano erupts today is the same way as it would erupt 1,000 years, 100,000 years, 1,000,000 years in the past. Thunderstorms, they behave the same way. So uniformitarianism, we can use that to knowing when some of these geological events happened, we will know how they occurred because by the principle of uniformitarianism, we will assume that they occurred the same way. The principle of original horizontality. Generally speaking, everything should be flat. Sediment layers will always start off horizontally. And so if rock layers, after the sediments harden and lithify, if rock layers are at an angle or a tilt, then something, geologically speaking, has happened to that area. There has been some type of disturbance. Perhaps there was a fault line that had some activity, or due to certain erosional features, the ground may have been shifted and tilted. So if rock layers are not horizontal, then some type of disturbance has happened in that area. The principle of cross-cutting relationships. When we take a look at the inside of the Earth, we can, with the rock layers, tell when things occurred. So any rock formation is going to be younger than the rock that cuts through it. So in the two diagrams here, on the diagram on the right side, with the layers A, B, and C. So first, of course, due to horizontality, I know that layer A was laid down first, layer B, the pink layer, was laid down next, and then layer C was laid down. We have a little bit of erosion, which shows the little chunks there. Then I know that the injected magma, layer D, came through. How do I know that that came forth? Because it cut through layers A, B, and C. And then the newest event that happened in this area was the little fault line, or E, that cuts through all of the layers and the injected magma as well. In the diagram on the left, I know that my layers A, C, F, G, and H were laid down. Then we have the intrusion B that comes across. Then after that came through, a fault line D shifted everything. So I know that because of cross-cutting relationships, you can sequence the rocks. Unconformities are kind of like missing pages in a book. If the geologic time scale were like Earth's autobiography, if it could write a book about itself, there would be some missing pages and missing chapters. Because we have weathering and erosion, if there are any fossils or any evidence of a geological or astrological event that has occurred, if that rock has eroded away, that information is gone. And so unconformities are gaps in the rock record that we have from erosion. The fossil record, of course, is the best physical evidence that we have have remains of ancient organisms that lived long before humans got on the planet. Fossils are remains or traces of an ancient or once living organism. Fossils do not always have to be bones. They can also be tracks or prints. They can be leftover nesting sites. Anything that proves that something was living at one time can be considered a fossil. And so we use fossils to kind of correlate or match different events around the world. So we can take matching rock units from different regions, and paleontologists use what they call index fossils to correlate or match this information. Index fossils are like the poster fossil for a particular time period. They're useful to estimate time markers. Index fossils are common globally, and they are very specific to a part of the geologic time scale. And so we can match different events from area to area using correlation. So the geologic time scale is, like I said, if Earth could write a book about itself, it would be the geologic time scale. It shows both biological and geological changes in the fossil and the rock record. It is the best physical evidence that we have of life existing on the planet. Now, when we talked about relative dating and talking about generally getting a ballpark estimate of the age of objects or events, scientists really want to know a more accurate age. And so we can use what's called absolute dating. Sometimes absolute dating is also called radiometric or radioactive dating. But absolute dating assigns a precise age to an organism, an object, or an event. And we can use this information by taking a look at the amount of radioactive material versus stable material in an organism or an object or an event. So radioactive isotopes are very handy dandy for scientists to use for absolute dating because radioactive isotopes decay at a very constant rate. It's almost like a clock. And so geologists use that constant rate to measure a more accurate age to the rock or fossil. And they do that by using what's called the half-life. The half-life of an isotope is the amount of time it takes for half of that isotope to decay and become stable. All radioactive isotopes don't want to be radioactive. They want to be normal, they want to be stable. And the reason why they're not normal and stable is because they have extra particles. And so radioactive isotopes will shake and vibrate and wiggle and throw off their extra particles at a very constant rate, like a clock. So geologists can count how many half-lives have gone by, seeing how much radioactive versus how many stable elements there are in that object or event. Probably one type of radioactive or absolute dating that you're probably familiar with is what we call carbon dating or carbon-14 dating. Carbon-14 is a radioactive isotope of carbon, so it is found in all living things. You and I also have carbon-14 radioactive elements in our bodies. It takes 5,730 years for half of the amount of carbon-14 in our bodies to change to nitrogen-14, which is the stable element of carbon-14. So if we find a new caveman and unearth that, we can, using absolute dating, get a very accurate estimate of the age that the caveman died, using the amount of carbon-14 versus nitrogen-14 in a sample. This has been Physical Science 2, Chapter 21, Part 4 on the Earth's changing surface.